All right, welcome to MAE 242 Recitation 6. In this session, we're going to be going over a little more control volume stuff and also one more force on a curved object one at the very end. So it'll be nice. You guys have your exam coming up on Wednesday. So this is a pretty good little synopsis of what'll mostly be on the exam. So yeah, let's get into it. So for this first one, we have an incompressible fluid flows past an impermeable flat plate with uniform inlet profile U equals U naught and cubic polynomial exit profile that's given by this equation right here, this function, right? Where U at any given Y, right? Y location up here, it's given by this function U naught times 3 eta minus eta cubed all over 2, where eta is just Y over delta, and delta is the height of the control volume. We want to compute the flow, the volume flow rate Q across the top surface, and the width is B into the page. All right. So as far as assumptions and stuff go, they really give us most of the stuff, so I'm not going to harp on that. The only additional one, let's say additionally, d by dt equals 0. It's a steady, right? Steady flow. And you could also say it's inviscid, right? Even though you don't really care, because just from the jump, you can tell by what they're asking us to find, right? We want to compute some volume flow. We're not dealing with any forces at all. So all we're gonna do is mass conservation here. So as far as calling it inviscid, you're not dealing with forces anyway. It doesn't really matter too much. But it's also important to know if you don't know, m dot equals density times volume flow rate equals rho times Q. All right, we'll use that here in a sec. So let's really get into it, right? So the only difference with these ones compared to just your standard everyday control volume one is that in this outlet flow here, right, you can't assume that the m dot term is just rho VA, right? Because what's V? You don't know V. And, in the inlet flow, you can call V just a scalar value where it's, U naught. But the velocity coming out is changing at each little cross-sectional slice as you go up. So you go, all right, so what the hell is the velocity there? So that's where we have to keep in the integral form, okay? So that's the basis of this problem. And the other basis is, so you've got some, we can consider this like a linearly distributed load coming in, right? Where we have all of this mass coming in, and then it's a maximum velocity U naught, right? And coming out, we have the same maximum velocity U naught, but we've got this cubic velocity distribution. So you know that what is coming in and what's coming out are a different number. So you go, all right, so what's the final, what's the missing piece? And that's this m dot coming out, right? Where we want to compute this volume flow rate from this m dot that's coming out, because what's coming in and what's going out is not the same thing. So we have to account for it by this extra, mass flow coming out from the top, right? And this is where control volume analysis gets really powerful, because we don't care about what the dimensions of this top end are, right? We just know by virtue of concentration of mass that we're going to have some quantity flowing out, and it doesn't really, we don't really care about the dimensions of the top end. We're not going to use any sort of dimension stuff to compute that. We're just going to subtract stuff out. So let's get into it. So like I said, the only equation we're going to need here is our conservation of mass. So let's write that down. And for your exam, try and write the full equation for like mass and momentum at least once. Put it somewhere, right? Put it somewhere on your page. Show me that you know what you're doing. So we got this, right? Right, where like we said before, we can get rid of this time derivative term. Okay, so now let's break it into our, we've got our normal vectors here, yada yada. You guys know all that stuff. I'm not gonna harp too much on that. You guys should be familiar with this. So I'm just gonna move everything into like, the left-hand side is what's coming in, right-hand side is what's coming out, and like the m dot form. So what do we have coming in? Our m dot in is going to be on the left-hand side, it's just rho density times u naught times what's the height of our thing? It's b into the page and delta tall. So delta b is our area. And this equals some m dot top, right? That's coming out through the top. So I'll say m dot top plus m dot out, where m dot out is going to be the actual like integral form of this thing. So I'll just move this over. M dot top is equal to that rho, that density times q, what we're trying to solve for. And m dot out equals integral. So let's actually go and compute this, right? So let's take this integral. And what is this integral we're going to be doing? Well, let's look at this term, okay? So we've got some density. That's easy enough, right? And now this v dot n, well, all the velocities are always normal to the surface coming out, so that's fine. So every time we dot our little individual velocity with this n, it's still just going to be a positive number, right? So that's fine. So now we just end up multiplying by this whole u function, right? So let's go u naught times, it's 3 eta minus eta cubed over 2, right? So that's our velocity. Now, what's our area we're integrating over? Well, nothing's changing with respect to like as we go into the page, right? It's only changing as a function of y. So we can pull out that b term that's into the page. We can just call that a constant. And now what are we integrating with respect to? We're integrating with respect to y. So dy. And what are our limits? It's y equals 0 to y equals delta. Okay. So let's expand this a little more. Let's pull out some constants. We've got rho as a constant. We've got u naught as a constant. B is a constant. And now I'm going to rewrite it in the form of, I'm going to split these variables up, right? You do the little thing, right? Split the thing, split each term. And then I'm just going to sub in what like eta actually is, where it's, y over delta. So this first term will be, ooh, that was really gross. All right. This first term is going to be, 3y over 2 delta. The second term is going to be y cubed over 2 delta cubed, and then with respect to y, right? And so now go and math this out. Go plug it in. I'm not going to do the full integral sitting here, but it'll be like 5 over 8 rho u b delta, I believe. Delta b, u delta b delta, whatever. All right, so that's what m dot actually equals, right? Now go plug everything back in, right? Plug back in. And so what do we have on this left-hand side? We still just have our, rho u naught delta b equals, what's our m dot top? It's rho times q. And then what's this over here? Plus 5 over 8 rho u naught delta b. All right, go simplify out, factor out a density, right? So you get u naught delta b equals q plus 5 over 8 u naught delta b. Go math it out, solve for q, right? Subtract the 5/8 from that side. I'm getting q equals 3 over 8 u naught delta b. And the units of this would be in like, it's a mass flow. Not a mass flow, it's a volume flow. So it'd be like, cubic meters per second, cubic feet per second, yada, yada. Something in that similar vein. All right. Any questions for that? Everybody cool with that? What's up? Yes. I was late. Okay. For those listening in the video too, I was lazy and didn't write my assumptions down. Always write your assumptions down. Always write your assumptions down. I just didn't. The only additional assumption I made was like right here that d by dt is zero because it already tells it gave you all the assumptions in the problem where it said it's incompressible, impermeable, flat plate, uniform inlet profile. So I just didn't, for the sake of time, I was like, let's not bullshit around and write all that stuff down. Yes, on the and like on the exam, it'll be like a subpart of the question. It'll be like state your assumptions clearly and yada yada. Like it'll be they'll be clear. So yes, always write your assumptions down. Always draw your control volume. Again, I didn't hear because it was already like this diagram I drew was literally I took it straight from the PDF because I didn't have to want to flip back and forth with the computer. So literally, like this is the exact problem. It gave you the control volume already. No guarantees on the exam if they'll give you the control volume or not. I'd say probably not. You're just gonna have to sit there and live with it, but do it yourself. But yeah, like I mean, every little detail you can put in, please put it in. Like, I mean, even if it's something stupid and pedantic, like give me as much to grade as I can. I don't care. I'm not gonna dock you for putting too much. Anyway, cool. All right, anything else? Yeah, I mean, nothing crazy. It's just the same stuff we've been doing, but you just can't assume that every inlet and outlet is rho VA, right? You just have to remember it's actually an integral you're doing. And just by sheer coincidence and, simplicity that we can get everything down to rho VA. But really, it's nothing different. It's nothing too bad. All right, now moving on to this next one. This is a very arrow E kind of problem. It's kind of nice. Really, really gets me going. I'm an arrow guy. Let's go. Okay. So this one's pretty tedious, and I'll show you why that is in just a sec. So anyway, we have an oval-shaped body. It's mounted in a wind tunnel. Test section is rectangular with height 2h and width L into the page. The model spans the entire width. It is subject to a steady, uniform, incompressible inlet flow. So again, I'm not going to write all the assumptions down because it gives you like 90% of them, right? It's subject to a steady, uniform, incompressible inlet flow of V1. The pressure gauge indicates the pressure gauge this is pressure gauge. Pressure gauge indicates a difference between inlet and outlet. Inlet, outlet. The exit velocity profile is shown. Okay, it's shown. They show it to us, but they don't give us what that velocity profile is. Like last time, they just gave us a nice equation. I'll show you how to go about getting that equation. Okay. The exit velocity profile is shown. Yada yada. Find the force acting on the model in terms of V1, H, L, delta P, and rho. So we're gonna it wants us to find some force. So what are we gonna do? At some point, for damn sure, we're gonna have to use conservation of momentum. Cool. So again, I'll put additionally. Right, because it's steady with respect to time. So yeah, like I said, you're gonna have to be using mass for. So I know this flow. This is like the opposite case of what we were looking at before, where last time we had some airflow coming out like the top, right? Well, this is a wind tunnel, so everything's all closed off. So what's coming in for sure has to be coming out. And with that, again, we've got some like, uniform, you can call this like a uniformly distributed load if you like mechanics, right? You can call this quantity is coming in, and you've got some quantity coming out, but you've got all this empty space here in the middle. So you know that the Vmax velocity that's coming out on these edges up here has to be greater than V1 in order for all of this to be what's coming in equal to be coming out, right? Is everybody fine with that? So we've got to solve for this Vmax. Because if you go and do all these equations, you're going to be getting this Vmax floating around, and Vmax is not one of the terms we are given. It's totally unknown. So that's where you have to do your conservation of mass from. Now you go, okay, well, in order to find that Vmax, I need a velocity profile. And you're right, you do. We show it to you, but we don't give it to you. Okay. So this is a linear velocity profile. Linear velocity profile. And so with that, it can either be two things. Okay. So first off, just from the jump, like, oh, and I guess I'll write this. So this is H, and then let's get our axes going. This is X direction. This is Z direction. Okay. So at this outlet, right? We're gonna say V of Z is equal to something. We're gonna have some like ratio looking thing, okay? Because it's a linear velocity profile. So just from like triangles, as you go up the triangle, like it's just like a ratio of the height to rise over run, right? Rise over run. So it's to be some ratio multiplied by this V max. So be V max times something in parentheses. And there's two different types of things, two different relationships you can get with this, right? If it was the inverse of this situation, where it was like a cone coming out, where it was maximum velocity in the middle and then tapered down to zero at the edges, like coming out of a pipe, right? Because a no slip condition, the velocity right at the pipe edge has to be zero and it's max in the middle. This is the opposite of that. If it was that pipe flow one, it would be like one minus Z over H. In this case, it's literally just straight up V max times the ratio of Z to our height H, where H is just the total height of the thing, right? And so a little sandy check to make sure this equation's right. First off, is it linear? Is there any squared terms, cubic terms, anything like that floating around? No, it's just straight up. And second, plug in Z equals zero to this equation. At the center line of this wind tunnel, right? This test section, the velocity has to be zero. So plug in Z equals zero to this equation. You get zero over H is zero times V max is zero. And then plug in Z equals H, right? If you have Z equals H, this becomes one. And so at H, V max is one times V max. Boom. You're good. So this is our linear velocity profile right here. So now let's start solving. Okay, again, start with conservation of moment of mass, right? Conservation of mass. Oh, blah, that is not conservation of mass. That was conservation of momentum. I'm getting ahead of myself. CS. Okay, so same story. It doesn't matter. I messed up this. We don't care about this term anyway. But yeah. Okay. So now same story. Same story as like last time. I'm going to split this into m dot in and m dot out. M dot in is easy, just what you've always done, right? Left hand side, technically it's negative, but you flip to the left hand side, becomes positive. So M dot in is just what's our density? It's rho. What's our velocity? It's v1. What's our area? Well, it's 2h because we split this thing symmetrically in half. So it's 2h times the width L into the page. Okay, now equals this integral for the outlet. So what's this integral? You already know. Okay. And so let's also be smart about this too. You don't want to have to be integrating from like negative H to positive H and like do like sign flippy stuff, right? So let's just be smart about this. It's symmetric. So it's just multiply a two, multiply by two, multiply this integral by two, and just go from like zero to H. Okay. Easy enough. And we're going to take Z equals zero to Z equals H of, again, what's this integral? We've got density times what's this whole v equation again? We're dotting. Every velocity point vector here is going to be dotted with the positive end vector, right? It's just doing the same thing. It's just all positive. We're just going to have this whole term, v max z over h dz, or I need the L times L dz, right? Where L is still just that constant length into the page, and we're iterating with respect to z. So let's start simplifying. Rho v1 to hl equals, let's pull out all the constants here. So we have that 2 Density and Vmax are both constants. And also, the 1 over h is a constant. And then the L is a constant. So literally, now all you're just left with is 0 to h of z dz, right? Which, if you go and math this out, I mean, it's just h squared over 2. Not very tough. So go do all that stuff. Solve this. You get rho v1 2 hl. It's just the 2's end up canceling, and you just get rho vmax hl. Yeah, that's what this whole integral simplifies down to. So now start factoring stuff out. So you got density goes away, h goes away, l goes away. You get vmax equals 2v1, which is good. That's nice. So cool, right? So look, we've defined vmax in terms of one of our given variables. So we're ready to go. We're ready to move on to the next part. All right. So let's move on to conservation of momentum, which gets a little more tedious, but it's still all the same. Okay. So what's our conservation of momentum? We can't ignore pressure. So we're gonna have to do something about that. And you can see this written in a lot of different ways, I'm sure. I'm sure you've seen a lot of different stuff at this point. I'm going to be writing the pressure forces as like external force, right? So let's get our external forces going, okay? So if you think about this logically, right, we've got all this air coming in here, right? We've got all this air hitting this airfoil thing. So this force, this external force we're going to be solving for is going to be like that, right? Equal and opposite kind of thing, you know, Newton's laws, whatever. So what's the first external force? We've got this negative FD, this drag force pointed in the negative x direction. So minus FD, okay? And then what's our other external force? It's the pressure forces. So I'll say plus FP equals, again, that goes away. And so now we just have this CS term, right? Of, you know, yada, yada, blah, blah, blah. What I want to do, I want to find these pressure forces first. All right. Where FP equals, you know, you've got some pressure vector, you know, some pressures pushing up on this side, right? And then some more pressures pushing over on this side, right? So thinking about it in, you know, what direction they're pointing, you have a positive P1 times, what's the area? It's 2H times L. And then minus P2, 2H times L, right? Because that's pointing in the negative x direction. Pretty easy. So let's plug those in. So we have negative FD plus P1 2HL minus P2 2HL equals, all right, so now the first momentum flux term, right, from the inlet, that's, again, pretty easy. You know, it's negative, it's an inlet. Well, it's it's dotted with the negative, you know, it's dotted. The dot n vector is negative. You guys know what I'm talking about. And, you know, this is a vector equation, but all we care about is x direction because there's no y component, so who cares? So negative rho will be v1 squared. From this, you know, it spits out v1 squared after you do all that stuff. Again, 2h times L. Right, now plus, what's our integral again? So we're going from z equals 0 to z equals h again of rho. Now, this is the same concept as we just did up here, right, where this is all positive dots. So this, again, just becomes v squared. But you have to think you're squaring this entire v term, right? This is the v you're squaring. So you're squaring this whole thing, right? And now I'm going to plug in what we just found for Vmax is 2v1. So inside this whole thing, you get 2v1 times z over h, ooh, but times z over h, right? Now you're squaring that whole thing, okay? The entire thing gets squared times, again, now the area it's L times dz, right? Oh, and yeah, you're multiplying by 2 again. Okay, so same exact thing as we just did before, except now you're just squaring the whole term and integrating again. So, the h squared would factor out, the 4v1 squared would factor out, density factors out, L factors out. So you get left with a z squared dz, which just, after you do the integral, it's, h cubed over 3, right? So go do all that stuff. Pretty basic integral. This is a pretty fair game for like what it'll be on an exam, I would say. It's not too bad. But anyway, so let's keep going. End up getting negative rho v1 squared to HL. Plus, this factors out to like a really nice, easy number. It's like 2/3. Let me look at my cheat sheet. Um, yada yada yada. Yeah, you get 2/3 rho v1 squared HL, which is pretty nice. So anyway, now yeah, we're just gonna keep going. We end up wanting to solve for this FD. Cool. So if you're on the ball, you can see since we want everything in terms of a pressure differential anyway, a delta P, this P1 and P2, they have the same 2HL. So we can call this P1 minus P2. That is our delta P, right? So let's keep going. I'm just going to call this delta P now. P1 minus P2 is delta P equals um, what's 2 minus 2/3? Is that 4/3? So we have minus 4/3 rho v1 squared HL, right? Solve for FD. All right, move that over there, move that over there. Equals 2 delta P HL plus 4/3 rho v1 squared HL. Right? Should be that. Yeah, I don't think I missed a sign anywhere. Should be some of that. If I simplified wrong, my bad. Go correct me later. I know for sure the fluids part of it's fine. Focus on the fluids part of it. If I did my algebra wrong, hey, my bad. I do this stuff quick. Anyway, any questions for that? Again, it's not like super complicated. It's just one extra little tweak that you've got to worry about. It's not terrible. So yeah, pretty much. Yeah, you're not gonna have to worry about like gravity and viscosity and stuff. You don't worry about that. Yeah. Cool. Okay. Anything else? Okay, we've got one more super easy one. And it's kind of annoying how easy it is. Because it's quick. It'll take me literally 3 minutes. Check this out. So, the third one, we've got a quarter circle gate is hinged at C. Find the horizontal force P required to hold it in place. Neglect the width of the gate. The width is 3 meters. So this is literally like the freaking easiest force on curved surface problem you can imagine. If you see this on an exam, first off, I envy you. When I took this class, we had a way harder one than this. But yeah, this one's super basic. Let's just get into it. You guys know all the basics of how to do this one. So first off, I always find the horizontal force first. This is just way easier. FH is rho G height of the centroid of the projected area, right? In this case, this projected area that you're looking at horizontally is just a rectangle, So the height of the central will just be 1 meter, right? Times the projected area, which again is just a rectangle. So it'll be the height of the thing times the width of the thing. So plug in the numbers. We're going to use 998 because who cares? Times 1 times 2 times 3. And this should spit out. I've got some written down here. I'm sorry. Yada, yada, blah, blah, blah. This will be 58,740 newtons. Now, where does this act at? Okay, since this is like, you can think of this as like a, triangle load right here. And, it just acts 1/3 from the big end. So it's acting 2/3 meters from C. That's kind of a bad 3. 2/3 meter from C. Cool. Now, vertical force. Again, this is the easiest one you can do. So this is just rho times gravity times volume. In this case, it's just the volume of the water, right? So again, multiply everything out. 998 times 9.81. When it's a quarter circle, so what's the area of a quarter circle? It's just a quarter of a circle. So it'll be 1/4 pi times radius squared, so 2 squared, times the width, so times 3. And again, go plug this number in. It'll be a significantly larger number, like 90 something thousand. 92,270. And this is downward, right? That's downward at it'll be 4r over 3 pi from C to the left. And plug this in. It'll be like 0.849 meters or something. Yeah, 0.849 meters. Okay, so now we're ready. Take sum of moments about point C, solve for P. All right, now what we got up top here, we got a minus 2P. And then here, our horizontal force, that'll be pushing that away to our left. So we have plus 2/3 times FH. I'm not going to plug in the numbers. You guys can plug in the numbers. And then again, now acting down to the left of C, like that. So we have plus 0.849 FV, right? Go plug everything in, solve for P. Get P equals, what does P equal? It's like 50,000, 58,700. And you are done. Not too bad. Any questions with that one? That's a real basic one. Real basic. I mean, 2.5 minutes tops if you know what you're looking at. Not bad. Okay, everybody cool? All right, good luck on y'all's exams on Wednesday. It'll be fun.